Hello students, welcome back. Now let's go to binomial approximation of normal distribution. What is binomial distribution? It's an independent repetition of Bernoulli distribution. So we have 1 for success, 0 for failure, nothing else, and then just repeat it independently. Kind of like rolling a die many times. 1 for ace, everything else 0. Or toss a coin many times. 1 for head, 0 for tail, nothing else of course. Select a ball from an urn, 1 for say blue ball, 0 for any other color, and repeat many times. Those kind of things. Now if you sum them all up, like number of aces and rolling a die many times, that's binomial sum. And the expected value is NP, and the standard deviation is square root of NP1 minus P. Now from here, if you divide by n, then you get binomial average. NP divided by n, so we get just P. And this one here, divided by n, is equivalent to dividing by n squared from the inside of the square root. That's why we get n down here. As for the derivation of these formulae, I'm not going to talk about. Let's talk about just the use of those. All right, here's an example. According to Federal Highway Administration's 2007 statistics, the percentage of female drivers has just surpassed the percentage of male drivers in the United States. 50.2% are females. Suppose that a random sample of 20 drivers is selected for a survey, and use the normal approximation to estimate the probability less than half of the selected drivers are female. B. Use the binomial distribution to calculate the probability that less than half of the selected drivers are female. Let's do the second one first. For binomial, so we get this computation. Does it make sense? Let's see, less than 10 is same as 9 or less. So you calculate this binomial probability, 20 choose k, success, 0.50 to the k power, and failure, 1 minus that to the 20 minus k power, and repeat it from 0 female, 1 female, up to 9 females. It says less than half, so it goes up to 9, not 10. Less than or equal, then you go to 10. But it's less than half, so that's the computation. All right, that's binomial. Now let's consider normal approximation. First solution is to use binomial sum. And second solution is to use binomial average. Do they make difference? Actually, they do. And which is more accurate? Whenever possible, this is more accurate. But of course, this is more convenient. So when n value is big, then it doesn't make much difference. So we go with more convenient case. But here, in this case, n value is not really big, just 20. It's not like 2000, you see. So we'll have to do this, and this is going to be trickier. So let's do easier one first. Binomial average. So let's do normal distribution, and x is less than half. Either way, in this case, less than or equal to make no difference because this is a continuous random variable. So this causes a bit of a difficulty. So how does this thing work? Well, here we go. So here is a normal approximation picture, and then 0.502, 50.2%. So 0.502 is the expected value, and 0.5 is the half. So less than half is gonna be this area. So I exaggerated, but the distance between these two is actually very, very small, you see. And you have to calculate the z-score accordingly. So this is going to be 0.502 minus 0.5 minus 0.502, x minus mu, end minus center. And then down here, you have to calculate the standard deviation, which is 0.502 times 1 minus 0.502 over 20. Oh my, I am running out of space. Calculate this value, you're going to get z-score. And then based upon that z-score, you can look up the table and do your computation. You're going to get something. Ready? Let's go ahead and do that. So z-score is, approximately speaking, 0.5 minus 0.502 divided by square root of 0.502, 1 minus of that, divided by 20. That's my z-score. Let Mathematica calculate it. What do you get? I get, something very small. Negative 0.0178. So this is what I have to look up from the normal table. Is that right? Did I calculate everything correctly? Yeah, I guess so. 0. Okay, all right. And then from the normal table, what do I get? Let's see. Negative of 0.02 0.4920. 0.4920. So the probability is this is what we get. Let's see. Let me make sure if this computation is correct, because this number I got from binomial average, normal approximation, and this one I got from direct binomial computation are very different. Is there anything wrong? No, I don't think so. This is how it's supposed to be. So normal approximation appears not going very well, as a matter of fact. When n value is really big, it's gonna be okay, but for just 20, it doesn't look too good. But still, let's take it here. And now let's consider the other one, binomial sum. Is that better? Normal approximation, x is less than 10 is, you see, half of 20 is 10, but less than half is less than 10. But there's a bit of a problem. Less than 10 versus less than or equal to 10 makes no difference as far as normal random variable is concerned. So you see, approximating this one versus approximating x is less than or equal to, that makes no difference. That doesn't make much sense either. I mean, now let's consider this. I want less than or equal to 9, so let's consider this, less than or equal to 9. But then again, that's same as, less than 9 as far as the normal approximation is concerned, because this is continuous random variable. But then again, hey, I want less than or equal to 9, not less than 9. So how do we mend this situation? The industry standard is to go right in the middle. Let's take that. So you see, if you compare this and this, it looks okay, but that's equal to less than or equal to 10. Oh wait, that's not right. If you compare this versus this, it looks okay, but that's equal to less than 9. That's not right either. But if you go to somewhere in between, 9.5, now less than 9.5 or less than or equal to 9.5, in terms of continuous random variable, they make no difference, but they both fits this and also that. So that's where we're going to go. And that's something we could not do for binomial average. For binomial sum, yes, we can do. So, all right. So let's calculate the z-score this time. Oh, before that, no, let's calculate z-score. X minus mu over sigma, right? So X is 9.5 and mu is 0.052 NP, 20 times 20 NP. Now let me just take one more step. X minus NP over square root of NP 1 minus P. Okay, let's take extra step. Square root of N, 20, and P, 0.502, and 1 minus 0.502. So previously, we had P, 1 minus P over N. We have N times P times 1 minus P. A bit of a difference, but that's binomial sum, that's binomial sum versus binomial average. Not much of a big deal. But here, instead of 10, I'm using 9.5. That's a big difference. All right, let's resume our computation. What is this if you use Mathematica to calculate? I'm using .7 something, excuse me, something is not right here. Oh, 0.052 is wrong. 502. Okay, all right. 502, 50.2%. Okay, the others are all correct. All right, this makes sense. negative 0.24 something. Okay, look up negative 0.24 from the z table and let's see what you get. Negative 0.24, negative 0.2, 0, 1, 2, 3, 4. So 4052, 0.4052. See that? 0.4052. Therefore, the probability, the normal approximation of this probability, which, oh, it's already here. So that's approximately equal to, and what was the number again? 4052. So I don't need this anymore. I don't need this anymore. Now compare this with that. It's not bad at all, right? If you use binomial sum, then, if you use a normal approximation of binomial sum, then the straight ahead computation for binomial distribution, that comparison yields pretty good approximation. If you just use binomial average, it's not very good. And this is equivalent to actually just using 10 here. If you use 10 there, then you're going to get something really bad. Let's see. Yes. You see, negative 0.01788, that's the figure we got before. So this binomial average is simple because I don't really have to consider 0.5, but the trade-off is it's a bad approximation. Now this binomial sum method is a little bit harder because I have to consider this 0.5. But it gives you a good approximation. Now let me open up this answer key here. What did I do? Yes, I just used binomial sum here. And yes, I have this normal picture and then 0.40458 something, which is pretty close to what we have over here. And then, oh, this is probability histogram for binomial, which looks very much like normal. L-shaped. I don't need these two anymore. Excuse me, before erasing, let me show you one final comparison. Binomial average, you don't really need 0.5, so that's easier to apply, but it's not a good approximation in general. Binomial sum, you have to use 0.5, so it's harder to apply, but it gives you a good approximation. Now, if your n value is big, instead of 20, we just have 2000, for example, then it's okay to do it this way. Okay, so much for the theory and an application problem on binomial. And we'll probably do one more exercise about binomial approximation in a separate video. Stay tuned.